13 billion years ago, before Earth existed, before our star ignited, galaxies were already shining in the void. NASA just found them. Massive, mature, impossible galaxies that challenge everything we thought we knew about cosmic birth. We are about to journey to the absolute edge of reality, where light itself runs out, where time behaves strangely, and where the universe reveals secrets it was never meant to show us. If you enjoy exploring the cosmos, hit that like button and subscribe to join us on this journey. Prepare yourselves. We begin. The James Webb Space Telescope captured something impossible. Light that began traveling before our planet formed, before our star existed, before anything we recognize as familiar came into being. This light traveled for 13 billion years through expanding space, through voids and galaxy clusters, past dying stars and forming worlds, until it finally hit the golden mirrors floating above Earth's atmosphere. When astronomers analyzed this ancient signal, they realized they were looking at a photograph of the infant universe. The photons carried information about galaxies that existed when everything was young, when the cosmos itself was still figuring out the rules of physics. Think about holding a message in a bottle that crossed an ocean so vast, it took longer to traverse than all of human history multiplied 1,000,000 times over. The telescope works by collecting infrared light, the stretched and tired remains of what was once bright and energetic. As space expands, it pulls light waves apart like taffy, shifting them from blue to red, from visible to invisible. Webb was built specifically to see this transformed light, to peer back through time itself. Every second, ancient photons rain down on us from every direction. Most pass through our bodies unnoticed, but Webb catches them, focuses them, and translates them into images that reveal what the universe looked like when it was only a few 100 million years old. For context, if the universe were a human lifetime of 80 years, we are now looking at baby pictures taken when it was just 2 years old. The data reveals galaxies already shining brightly, already organized, already massive. According to previous models, the universe at that age should have been mostly dark, with small clumps of matter just beginning to gather. Instead, Webb shows us a cosmos already alive with structure and light. The implications shake the foundations of cosmology. Scientists measure distance in space by measuring time. When we say something is 13 billion light-years away, we mean the light took 13 billion years to reach us. We are not seeing that object as it is now. We are seeing it as it was, frozen in a moment from the deep past. That galaxy might have evolved beyond recognition, or collapsed into a black hole, or collided with neighbors. We cannot know. This discovery means our timeline of cosmic evolution needs revision. Galaxies formed faster, grew larger, and became more complex much earlier than anyone predicted. The universe was not a slow, gradual construction project. It was an explosion of creativity and structure right from the beginning. But what Webb revealed in that ancient light raises an even stranger question. If galaxies already existed in such mature forms so early, what came before them? What invisible processes shaped the universe in its first few 100 million years, before light could even travel freely? The answer lies in the next discovery, and it defies everything we thought we understood about how cosmic structures form. Astronomers found galaxies hiding in the data, where their equations said only darkness should reign. These structures appeared fully illuminated, fully formed, sitting comfortably in a time period when the universe supposedly lacked the ingredients to build them. The standard model of cosmology predicted these regions would be empty, still waiting for matter to clump together enough to ignite the first stars. The shock came from the sheer number of mature galaxies, not one or two anomalies that could be explained away as flukes. Dozens of them, hundreds of them, scattered across observations of the early cosmos, like cities appearing on a map of wilderness. Each one represented a violation of the timeline scientists had spent decades constructing. According to established physics, galaxies form through a slow process. First, Dark matter creates gravitational wells. Then hydrogen gas falls into these wells. The gas compresses under its own weight. Eventually, it reaches temperatures and pressures high enough to trigger nuclear fusion. Stars ignite. Those stars cluster together. Over hundreds of millions of years, they organize into rotating spiral or elliptical shapes we call galaxies. This process requires time. The universe expands during this construction, spreading matter thinner, making it harder for gravity to pull things together. Early calculations suggested the first proper galaxies would not appear until the universe reached at least 500 million years old, maybe older. Webb shattered that timeline by finding fully functional galaxies at 300 million years, at 200 million years, even earlier. Imagine predicting it takes 10 years to build a skyscraper, then finding completed skyscrapers everywhere after just 3 years. The construction schedule does not add up. These galaxies were not small or primitive either. They contained billions of stars already burning through their fuel cycles. They showed signs of chemical enrichment, meaning multiple generations of stars had already lived and died inside them, spreading heavy elements through their gas clouds. This level of complexity should require far more time than the universe had provided. The discovery forces uncomfortable questions. Either our understanding of how galaxies form is fundamentally wrong, or something happened in those early moments that we completely missed. Perhaps dark matter behaved differently in the infant universe. Perhaps gravity worked more efficiently when everything was compressed closer together. Perhaps some unknown force or particle accelerated the formation process. One possibility involves primordial density fluctuations. If the Big Bang created regions where matter was already slightly more concentrated, gravity could have pulled things together faster than expected. But the fluctuations required to explain what Webb sees would be much larger than what we observe in the cosmic microwave background, the afterglow of the Big Bang itself. Another explanation suggests our measurements of time and distance might be slightly off. If the expansion rate of the universe changed more dramatically in the past than we think, objects we believe are 13 billion light-years away might actually be closer, and therefore younger than we calculate. This would give them more time to develop. Neither explanation feels satisfying. Both require rewriting fundamental assumptions about cosmic evolution. The galaxies sit there in the data, undeniable and real, refusing to conform to predictions. Yet the mystery deepens even further when we examine not just where these galaxies exist, but what they look like. Their structure reveals something even more troubling about our cosmic models. The galaxies staring back at us from the edge of time show sophisticated structure. Spiral arms curve elegantly outward from central bulges. Elliptical shapes glow with evenly distributed starlight. Bar structures channel gas toward galactic cores. These features suggest billions of years of evolution and gravitational sculpting, yet they appear in cosmic infants barely out of the womb. Our own Milky Way galaxy took over 10 billion years to develop its current appearance. The spiral arms formed gradually as stars orbited the center at different speeds, creating density waves that compressed gas and triggered new star birth. The central bulge grew as stars migrated inward over countless rotations. The entire system evolved through mergers with smaller galaxies, each collision adding mass and complexity. When we observe nearby galaxies in the present day, we see a clear progression. Young galaxies look chaotic and irregular, their stars scattered randomly, their shapes amorphous and undefined. Middle-aged galaxies begin showing organization, with hints of spiral structure or elliptical symmetry. Old galaxies display the refined beauty of mature systems that have had time to settle into stable configurations. This progression makes physical sense. Gravity needs time to organize matter. Random motions need time to settle into ordered rotation. Star formation needs time to move through multiple generations, enriching the galactic environment with heavier elements that enable different types of stars and planetary systems. But the ancient galaxies Webb discovered skip this entire developmental arc. They appear already organized, already mature, already displaying the features that should take billions of years to emerge. Imagine opening a time capsule from 100 years ago and finding a modern smartphone inside. The technology should not exist yet. The structure of these galaxies tells us about their internal dynamics. Spiral arms mean the gas is rotating in an organized disk. That organization requires the galaxy to have settled down after its initial formation, shedding excess energy through various processes. Central bulges mean stars have had time to migrate inward, pulled by the gravitational influence of the galactic core, and possibly a central black hole. Some of these ancient systems even show signs of past collisions and mergers. We can detect tidal streams of stars, faint trails of material pulled out during gravitational interactions between galaxies. These features serve as fossil evidence of violent encounters. Yet, for such encounters to have already occurred, multiple galaxies must have formed, grown large enough to survive collisions, found each other in space, and completed their destructive dance all within the first few 100 million years of existence. The timescale problem becomes more severe with each detail we examine. Every feature we see requires processes that, according to our understanding, should take much longer than the age of the universe at that point. Either these galaxies experience some kind of accelerated aging, or our clocks measuring cosmic time are badly miscalibrated. One radical proposal suggests we are observing galaxies that formed in a completely different way than modern galaxies do. Perhaps in the dense, hot environment of the early universe, matter could collapse directly into large structures without going through the slow hierarchical assembly we see today. This would be like a building appearing fully constructed in one moment rather than being assembled brick by brick. But even this idea faces challenges. The physics governing gravity, gas dynamics, and star formation should work the same everywhere and every when. The same laws that shape galaxies today should have shaped them 13 billion years ago. Unless those laws change, or unless we are missing something fundamental about how the early universe operated, what we found next makes this mystery even more disturbing. One galaxy in particular broke every record and expectation. Sitting in the data from when the universe was barely 500 million years old, this monster contained more mass than our entire Milky Way. Not similar mass, more mass. In a cosmic infant, the Milky Way has spent over 13 billion years accumulating its current mass of roughly 1 trillion stars, plus vast clouds of gas, dust, and the invisible dark matter holding everything together. It grew through countless mergers with smaller galaxies, each one adding new material to the growing structure. It captured gas from intergalactic space, converting it slowly into new generations of stars. The process was gradual, methodical, efficient. This ancient giant apparently skipped that gradual approach entirely. In less than 5% of the time the Milky Way took to reach its current size, this early behemoth had already surpassed it. The implications challenge everything we understand about mass accumulation in cosmic structures. Think of it this way. Imagine someone showing you 2 bank accounts. One person has been saving money for 40 years and has accumulated $1 million through steady deposits and compound interest. Another person has been saving for 2 years and already has $1.2 million. Either the second person found a completely different way to earn money, or the rules governing wealth accumulation changed dramatically between the two scenarios. Galaxies accumulate mass through specific mechanisms. They pull in gas from their surroundings through gravity. That gas collapses and forms stars. They collide with and absorb smaller galaxies in their neighborhood. Over vast timescales, these processes build massive structures, but each mechanism has limits imposed by physics. Gas can only fall inward at a certain rate before heating up so much it gets blown back out by radiation from forming stars. This creates a natural speed limit on galaxy growth. Mergers can only happen when galaxies encounter each other, which requires time for them to move through space and find each other. Star formation can only proceed as fast as gas clouds can cool and collapse under their own weight. These natural limits should have prevented any galaxy from reaching Milky Way mass within the first billion years. Yet here one stands, in defiance of every calculation. Either the early universe provided conditions that removed these limits, or we misunderstand the limits themselves. Some researchers proposed that this massive galaxy formed in an unusually dense region of space where matter was already concentrated from the beginning. If the initial conditions packed more material into a smaller volume, gravity would work faster, pulling everything together before expansion could spread it too thin. This could accelerate the entire formation process. Others suggested the galaxy might have formed through direct collapse of a massive gas cloud, bypassing the normal bottom-up assembly, where small structures merge to create larger ones. In this scenario, an enormous hydrogen cloud simply fell inward all at once, creating a giant galaxy in a single catastrophic event rather than through gradual accumulation. Both ideas require special circumstances that should be rare, yet Webb keeps finding massive galaxies in the early universe, suggesting these special circumstances might have been common, even typical. If so, our entire framework for understanding cosmic evolution needs reconstruction from the ground up. The mass of this single galaxy raises another question that cuts even deeper. Where did all that matter come from originally? The universe started as a nearly uniform sea of hydrogen and helium. Something had to gather that material into concentrated clumps, something powerful enough to overcome the expansion of space itself. The answer involves objects so extreme they warp space and time around them. Quasars burn at the edge of the infant universe with the light of 1 trillion stars compressed into a region smaller than our solar system. These are not galaxies. These are the hearts of galaxies, visible across the entire observable cosmos because of their incomprehensible brightness. Nothing else in nature produces this much light from such a small space. Each quasar marks the location of a supermassive black hole actively feeding on surrounding matter. As gas spirals inward toward the event horizon, it accelerates to nearly light speed, heating to millions of degrees through friction and compression. This superheated material radiates across the entire electromagnetic spectrum before finally crossing the point of no return and vanishing into the black hole forever. The energy output staggers the mind. A single quasar can outshine its entire host galaxy by factors of 100 or more. It can be visible from billions of light years away, while individual stars in that same galaxy remain completely invisible. If you placed a quasar at the distance of our nearest star, its radiation would obliterate Earth instantly. Webb detected dozens of these cosmic beacons shining in the early universe, when everything was supposedly still dark and cold and unorganized. Each one represents a feeding black hole, which means each one represents a black hole that already exists and has already gathered enough mass to power such extreme emission. The timeline problem that plagued early galaxy formation becomes even worse when we consider these quasars. The black holes powering these ancient quasars contain masses equivalent to hundreds of millions, sometimes billions, of our star. They sit at the centers of young galaxies, already mature, already active, already devouring matter at prodigious rates. According to standard black hole growth models, building such massive objects should require several billion years at minimum. Black holes grow by consuming matter. Every atom they swallow adds to their mass. The more massive they become, the stronger their gravitational pull, the faster they can gather new material. This creates a feedback loop where growth accelerates over time. Sounds like it should be fast, right? Wrong. There is a natural speed limit called the Eddington limit. As matter falls toward a black hole and heats up, it emits radiation. That radiation pushes outward against incoming material. At a certain feeding rate, the outward radiation pressure exactly balances the inward gravitational pull. The black hole cannot eat any faster without blowing away its own food supply. If a black hole grows at the Eddington limit continuously without stopping, starting from a single star mass seed, it would take about 800 million years to reach 1 billion stellar masses. The universe was not 800 million years old when these quasars existed. It was 200 million, 300 million, maybe 500 million years old at most. The math simply does not work. Either these black holes started much larger than stellar mass, or they found ways to exceed the Eddington limit, or time itself behaved differently in the early universe. All three possibilities require new physics or new understanding of extreme conditions. Some theories suggest these supermassive black holes formed directly from collapsing gas clouds in the early universe, skipping the normal pathway where stars form first, then collapse into black holes, then merge into larger black holes over billions of years. Instead, enormous clouds containing tens of thousands or millions of stellar masses might have collapsed straight into black holes during the first moments after the Big Bang. The presence of these ancient quasars tells us the universe was already violent and extreme in its infancy. What we discover next proves the early cosmos left permanent scars we can still see today. The numbers refuse to make sense. Black holes containing the mass of 1 billion stars existed when the universe itself was younger than our own star is now. These gravitational monsters had already consumed enough matter to outweigh entire dwarf galaxies, had already grown to sizes that should require billions of years to achieve, had already settled into the centers of forming galaxies like ancient kings on thrones. Our star is roughly 4.5 billion years old. The universe, when these black holes existed, was only 300 to 500 million years old. If we scale this down, imagine finding a human adult who claims to be 3 months old. The growth rate required defies biological possibility. The same impossibility applies to these cosmic giants. Scientists traced backwards through the math, trying to find a pathway that allows such rapid growth. Starting with the smallest possible seed, a black hole formed from a single massive star, they calculated maximum growth rates. Assuming the black hole fed constantly at the theoretical limit, the timeline still falls short by hundreds of millions of years. This led to increasingly exotic proposals. Perhaps the first black holes did not form from stars at all. Perhaps in the dense, hot conditions immediately after the Big Bang, regions of space collapsed directly into black holes without ever passing through a stellar phase. These primordial black holes could start with masses thousands or even millions of times larger than stellar black holes, giving them a massive head start on growth. Another idea involves supermassive stars that could only exist in the early universe. These hypothetical monsters would contain hundreds of thousands of stellar masses, burning through their fuel in just a few million years before collapsing directly into enormous black holes. Such stars cannot form in the modern universe, because the gas now contains heavy elements that cool the collapsing cloud, preventing it from reaching such gigantic sizes. But in the pristine hydrogen and helium of the infant cosmos, nothing would stop these titans from forming. Even with these proposals, the feeding problem remains. A black hole might start large, but it still needs to consume vast quantities of matter to reach billions of stellar masses. Where does all that food come from? The early universe was denser than today, which helps, but the material still needs to find its way to the black hole, spiraling inward through accretion disks, losing energy and angular momentum before it can fall past the event horizon. The environment around these early black holes must have been extraordinarily violent, gas clouds colliding at thousands of miles per second, shockwaves propagating through the surrounding medium, intense radiation from the accretion disk heating everything within light years to millions of degrees. Any planets trying to form in these regions would be sterilized instantly, their surfaces scoured by radiation powerful enough to strip away atmospheres and boil oceans. Yet these black holes somehow not only formed but thrived. They became the gravitational anchors around which entire galaxies assembled. Modern observations show that nearly every large galaxy has a supermassive black hole at its center, and the mass of that black hole correlates tightly with the mass of the galactic bulge surrounding it. This relationship suggests black holes and galaxies grow together, influencing each other through a cosmic dance that shapes both partners. If the relationship held in the early universe too, then these billion-mass black holes should sit inside correspondingly massive galaxies, which brings us back to the same problem from different angles. Massive galaxies forming too early, massive black holes forming too early, structure appearing before the universe should have had time to build it. The only way to solve this puzzle is to look even further back, to the moment when the universe first allowed matter to exist in stable forms. That moment left behind evidence we can still detect today, painted across the entire sky in invisible light. Microwave radiation fills every cubic inch of space, invisible to our eyes but detectable by specialized instruments. This faint glow represents the oldest light in the universe, released when the cosmos was only 380,000 years old. Scientists call it the cosmic microwave background, and it provides the most direct evidence we have of what the infant universe actually looked like. Before this moment, the universe was too hot and dense for light to travel freely. Photons scattered constantly off free electrons, unable to move more than a tiny distance before colliding with another particle. The cosmos was opaque, like trying to see through fog so thick it blocks everything beyond arm's reach. As the universe expanded and cooled, eventually the temperature dropped below a critical threshold where electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons could travel freely. The fog cleared, light streamed outward in all directions, and it has been traveling ever since. We detect that light today, red-shifted by cosmic expansion from visible wavelengths into the microwave portion of the spectrum. It arrives from every direction, forming a sphere around us that marks the edge of the observable universe. Mapping this radiation across the sky reveals temperature variations of about 1 part in 100,000. These tiny fluctuations might seem insignificant, but they encode the seeds of all structure that formed later. Slightly warmer regions corresponded to slightly denser areas of matter. Slightly cooler regions marked areas where matter was less concentrated. These density differences, though small, provided the gravitational seeds from which galaxies, clusters, and superclusters eventually grew. The precision of these measurements rivals anything in physics. Satellites like COBE, WMAP, and Planck mapped the cosmic microwave background with increasing accuracy, revealing details down to fractions of a degree across the sky. The pattern of hot and cold spots follows predictions from Big Bang theory with remarkable accuracy, confirming our basic understanding of cosmic evolution. Yet these same measurements create the problem we keep encountering. The size of the temperature fluctuations tells us how strong the initial density variations were. Those variations determine how fast structure can grow through gravitational collapse. When scientists run computer simulations using the measured fluctuations as starting conditions, the simulations predict galaxies should form much later than Webb actually sees them. The mismatch suggests something happened between the cosmic microwave background era and the first galaxy formation that our models do not account for. Some process amplified the initial density fluctuations, or gravity worked more efficiently than we think, or matter behaved in ways that accelerate structure formation. Without identifying this missing piece, we cannot reconcile what we see in the infant universe with what we measure in its baby picture. The cosmic microwave background also reveals the composition of the universe at that early time. By analyzing the pattern of fluctuations, scientists determined that ordinary matter made up only about 5% of the total energy density. Another 27% consisted of dark matter, and the remaining 68% was dark energy. These proportions appear to have remained roughly constant throughout cosmic history. Dark matter, despite making up more than 5 times as much mass as ordinary matter, interacts only through gravity. It passes through normal matter without colliding, without absorbing or emitting light, without leaving any trace except its gravitational influence. This makes it invisible to telescopes but essential for understanding how structures formed. The cosmic microwave background shows us the universe before the first stars ignited, before galaxies assembled. before any of the complex structures we see today existed. It captures a moment of simplicity before gravity began its long work of organizing matter. What happened during that organizational process reveals physics operating at scales we can barely imagine. The temperature variations painted across the cosmic microwave background hide patterns that reveal invisible architecture. When astronomers analyze these patterns statistically, they find evidence of acoustic oscillations, pressure waves that rippled through the primordial plasma before atoms formed. These waves left their fingerprints frozen into the distribution of matter, and we can decode them to learn about the early universe's composition and geometry. Imagine dropping a stone into a perfectly still pond. Ripples spread outward in concentric circles, carrying energy across the water's surface. In the early universe, random quantum fluctuations during cosmic inflation acted like stones dropped into the fabric of space-time itself. The resulting pressure waves propagated outward through the hot plasma at known speeds determined by the density and pressure of the medium. When the universe cooled enough for atoms to form, the waves froze in place. Matter that happened to be at the peaks of these waves when freezing occurred created the slightly denser regions we see as warmer spots in the cosmic microwave background. Matter in the troughs became the cooler spots. The characteristic size of these hot and cold regions depends on how far the waves traveled before freezing, which depends on the age and composition of the universe at that moment. Measuring the angular size of these spots across the sky allows scientists to calculate fundamental cosmic parameters with stunning precision. The data reveals the universe is geometrically flat, meaning parallel lines remain parallel forever rather than converging or diverging. It reveals the exact proportions of ordinary matter, dark matter, and dark energy. It reveals the expansion rate at that early epoch. These measurements create a standard ruler we can use across cosmic history. We know how large the acoustic features should be, physically based on the speed of sound in primordial plasma and the age of the universe at recombination. By measuring their angular size on the sky, we calculate the distance to the surface where the cosmic microwave background originated. This gives us an anchor point for cosmic distance measurements, a known reference against which we can calibrate other methods. The patterns also reveal where dark matter concentrated most strongly. Ordinary matter and radiation felt pressure from photons bouncing off electrons, which opposed gravitational collapse and caused the acoustic oscillations. Dark matter felt only gravity. It collapsed steadily into wells without oscillating, pulling ordinary matter along with it after recombination occurred and pressure effects stopped. This created a specific relationship between the height of peaks in the fluctuation pattern. Odd-numbered peaks correspond to regions where dark matter and ordinary matter collapse together. Even-numbered peaks mark regions where radiation pressure pushed ordinary matter outward while dark matter continued falling inward. The ratio between these peaks tells us exactly how much dark matter existed compared to ordinary matter. Every detail in the cosmic microwave background connects to fundamental physics. The polarization of the light encodes information about gravitational waves from inflation. The small-scale structure reveals how quickly the universe expanded during different eras. Large-scale patterns constrain theories about what happened before the Big Bang. Yet for all this precision and agreement with theory, the cosmic microwave background raises a troubling question. If the initial density fluctuations were as small as measured, if matter started out this evenly distributed, how did dark matter manage to create the gravitational scaffolding needed for rapid structure formation? The answer requires understanding how invisible matter shaped the visible universe before stars ever ignited. Invisible matter built the framework upon which everything visible hangs. Dark matter, immune to radiation pressure and electromagnetic forces, began collapsing into dense clumps, while ordinary matter still bounced around as hot plasma. By the time atoms formed and normal matter could fall freely under gravity, dark matter had already constructed gravitational wells waiting to be filled. Think of dark matter as the skeleton of the universe. Just as your skeleton provides structure that determines where muscles and organs can attach, dark matter created the gravitational architecture that determined where galaxies would form. It shaped the cosmic web, the vast network of filaments and nodes that gives the universe its large-scale structure. Everything we see occupies the scaffolding dark matter erected. The process began immediately after the Big Bang. While ordinary matter remained coupled to radiation through constant interactions with photons, dark matter experienced only gravity. This meant dark matter could start forming structures much earlier, when the universe was still too hot and dense for stars or galaxies to exist. By the time visible matter could finally collapse, dark matter halos had already grown massive. Computer simulations reveal how this unfolded. Start with tiny density fluctuations from the cosmic microwave background. Let dark matter particles move under gravity alone for hundreds of millions of years. They gradually flow toward slightly denser regions, making those regions denser still, which increases their gravitational pull, which attracts more dark matter in a runaway feedback loop. Massive halos form first. Smaller halos form around them. The structure grows hierarchically from the bottom up. These dark matter halos became the birthplaces of galaxies. As the universe expanded and cooled, hydrogen and helium gas fell into the gravitational wells created by dark matter. The gas collected in the deepest parts of these wells, compressed under increasing gravity, heated by friction and compression. Eventually, the cores reached temperatures and pressures sufficient to ignite nuclear fusion. The first stars turned on. Dark matter continues shaping galaxies today. When we measure the rotation speeds of spiral galaxies, we find stars orbiting far from the galactic center. They move much faster than they should. If only visible matter created the gravitational pull, they should fly off into intergalactic space. Instead, they remain bound to their galaxies, held by the invisible mass of dark matter halos extending far beyond the visible edges. Our own galaxy sits inside a dark matter halo containing perhaps 10 times more mass than all the stars, gas, and dust combined. This halo extends hundreds of thousands of light years into space, far beyond where any stars orbit. Its gravity holds the Milky Way together and influences how smaller satellite galaxies interact with us. In the early universe, dark matter halos provided the gravitational seeds that allowed rapid structure formation despite the small initial density fluctuations measured in the cosmic microwave background. Without dark matter, galaxies would have taken much longer to form, perhaps too long to explain what Webb sees at the edge of time. The relationship between dark matter halos and visible galaxies follows predictable patterns. More massive halos host more massive galaxies. The central density of the halo correlates with properties of the galaxy residing there. This tight coupling suggests dark matter and ordinary matter grew together in a coordinated dance despite experiencing completely different physical forces. Yet dark matter creates its own mysteries. We have detected its gravitational effects clearly, measured its abundance precisely, mapped its distribution across space. But we have never directly detected a dark matter particle. We do not know what it is made of. We do not know how it behaves except through gravity. And its presence reveals that most of the universe remains invisible to us, hiding in the spaces between stars. Between the galaxy clusters and superclusters, space opens into regions of almost perfect emptiness. These cosmic voids stretch across hundreds of millions of light years, containing almost no galaxies, almost no matter, almost nothing except the gradual expansion of space itself. Flying through one of these voids at light speed would take longer than all of recorded human history to cross from one side to the other. The voids were not carved out after the fact. They represent regions where matter was slightly less dense during the initial moments after the Big Bang. While gravity pulled matter together into filaments and nodes where galaxies formed, these underdense regions lost matter to their surroundings. As material flowed out toward denser areas, the voids expanded and emptied further. Now they dominate the volume of space, with galaxies clustered into thin shells and filaments surrounding vast bubbles of near-nothingness. Measuring these voids reveals information about dark energy and the expansion of the universe. As space expands, it carries galaxies away from each other. In dense regions where gravity strongly pulls galaxies together, this expansion can be overcome locally. Galaxy clusters remain bound despite cosmic expansion, but in the voids, nothing opposes expansion. These regions grow faster than the overall average expansion rate, pushing their few remaining galaxies toward the walls. The size distribution of voids depends sensitively on cosmic parameters. If the universe expanded faster, voids would be larger because matter would have less time to collapse into structures before expansion pulled it apart. If dark matter were more abundant, voids would be smaller because stronger gravity would prevent matter from flowing out of underdense regions. Mapping voids across cosmic history provides a test of our cosmological models. Some voids span more than 300 million light-years across. The Botas void, discovered in the 1980s, contains only about 60 galaxies where thousands should exist based on the average density of the universe. Flying toward its center, galaxies would become increasingly sparse, their light dimming as distance increased, until eventually you would find yourself surrounded by darkness in every direction, with the nearest galaxy millions of light-years away. Life inside a void would experience the universe very differently. Looking outward, you would see distant galaxies clustered along the edges like cities surrounding a massive empty plain. Looking inward, you would see nothing, just the cosmic microwave background radiation and perhaps a few isolated dwarf galaxies wandering through the emptiness. The night sky would appear nearly black, with far fewer stars and galaxies visible than we see from our position inside a galactic cluster. The voids contain some matter. Diffuse gas fills the space, though at densities millions of times thinner than even the best vacuums we can create on Earth. Dark matter passes through, though in concentrations far below the cosmic average. Occasionally, a galaxy finds itself inside a void, either because it formed there before all the matter drained away, or because it was ejected from a cluster and drifted into the emptiness. These void galaxies evolve differently from galaxies in dense environments. They experience fewer mergers because they rarely encounter neighbors. They maintain larger gas reservoirs because ram pressure stripping does not remove their fuel for star formation. They tend to be smaller and bluer than cluster galaxies, still actively forming stars while their counterparts in dense regions have exhausted their gas supplies. The existence of such large voids challenges our ability to simulate cosmic structure formation. Creating voids this empty requires moving enormous quantities of matter over vast distances in the time available since the Big Bang. The process involves complex feedback between dark matter, ordinary matter, and dark energy operating across the entire cosmic web. Stand back far enough, and the universe reveals its true architecture. Galaxies trace out filaments, like strands of a vast spiderweb stretching across space for billions of light-years. These filaments connect at nodes where galaxy clusters gather, massive gravitational anchors holding the structure together. Between the filaments, the voids expand. The entire pattern resembles neural networks or blood vessels, natural structures that maximize connectivity while minimizing wasted space. Computer simulations reproduce this web pattern perfectly. Start with the tiny density fluctuations from the cosmic microwave background. Let dark matter evolve under gravity for billions of years. The initial random variations amplify into a cosmic-scale foam of filaments and voids. Matter flows along the filaments like water through pipes, gathering at the intersections where massive clusters form. The simulation results match observed galaxy distributions with remarkable precision. The filaments themselves contain hidden mass. Most of the ordinary matter in the universe does not reside in galaxies. Instead, it fills the space between galaxies as diffuse gas heated to millions of degrees. This intergalactic medium is too hot to emit visible light, making it nearly invisible to traditional telescopes. But it radiates X-rays and absorbs specific wavelengths from background quasars, revealing its presence to specialized instruments. Following a filament from end to end would take hundreds of millions of years at light speed. Along the way, you would pass through regions where gas density increases, where temperatures fluctuate, where shock waves from ancient galaxy collisions still propagate through the medium. You would encounter galaxies strung like beads along the filament's length, their positions marking regions where the dark matter concentration became strong enough to trigger star formation. At the nodes where filaments intersect, galaxy clusters dominate. These are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, plus vast quantities of hot gas and dark matter. The Coma cluster, for example, contains over 1,000 galaxies within a region roughly 20 million light-years across. Its total mass exceeds 1,000,000 billion stellar masses, most of which exists as dark matter. The web structure emerged naturally from gravity acting on the initial density field. No external organizing principle guided it, no intelligence designed it. The same physics that causes an apple to fall from a tree-shaped structures across billions of light-years. This demonstrates how simple rules, applied across vast scales and timescales, create complex, emergent patterns. Tracing the cosmic web backwards through time shows it becoming more uniform and less structured. At the era of the cosmic microwave background, only the faintest hints of future structure existed as tiny fluctuations in density. By the time the first stars ignited, the web had begun to take shape, but remained much more diffuse than today. Over billions of years, gravity amplified the structure, making dense regions denser and empty regions emptier until the modern cosmic web emerged. The web continues evolving. Dark energy accelerates the expansion of space, which will eventually tear the web apart. Filaments will stretch and break. Voids will grow larger. Galaxy clusters will become increasingly isolated as the space between them expands faster than light can cross it. Trillions of years from now, the cosmic web will have dissolved into disconnected fragments separated by unbridgeable distances. But before that distant future arrives, we can observe the web in its current glory, a monument to how gravity shapes matter across cosmic scales. The web proves the universe has structure on every scale, from individual galaxies to the largest features we can map. And flowing along that web, galaxy clusters race away from us at speeds that defy intuition. Galaxy clusters at the edge of the observable universe recede from us at velocities exceeding the speed of light. This sounds impossible. Einstein's relativity forbids anything from moving through space faster than light can travel. Yet the observation remains true, and it reveals something fundamental about the nature of cosmic expansion that most people misunderstand. The key lies in distinguishing between motion through space and the expansion of space itself. When we say nothing can exceed light speed, we mean nothing can move through the fabric of spacetime faster than light moves through that same fabric. An object zipping past you at 99% of light speed obeys this rule. Its motion carries it through existing space. Cosmic expansion works differently. Space itself grows, stretching the distance between objects without moving them through their local region of spacetime. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart, but none of them slide across the rubber surface. The rubber itself expands, carrying the dots along for the ride. For nearby galaxies, expansion creates slow recession velocities. A galaxy 1 million light-years away recedes at roughly 70 kilometers per second due to expansion. Double the distance, double the recession velocity. This relationship, discovered by Edwin Hubble in the 1920s, reveals that expansion rate remains constant across space. Every megaparsec of distance adds approximately 70 kilometers per second to recession velocity. Now scale up to cosmological distances. A galaxy 1 billion light-years away recedes at roughly 70,000 kilometers per second, about 23% of light speed. A galaxy 10 billion light-years away recedes much faster, approaching or exceeding light speed, depending on exact distance and the expansion history of the universe. At 13 billion light-years, the recession velocity far exceeds light speed. These distant galaxies are not violating relativity. They remain essentially stationary relative to the space immediately surrounding them. But the space between us and them expands so rapidly that the cumulative effect produces faster than light recession. Think of two people standing still on opposite sides of a vast plane. If the plane itself stretches, growing wider at every point simultaneously, the people separate faster than either could run, even though neither moves their feet. This creates a cosmic horizon beyond which galaxies recede so fast their light can never reach us. Photons emitted toward Earth from beyond this horizon fight against the expansion of space. They make progress toward us in their local region, but the cumulative expansion between their starting point and Earth increases distance faster than they can travel. Like swimming upstream in a current faster than you can swim, they make no net progress. The exact location of this horizon depends on the expansion history and the current acceleration driven by dark energy. It sits somewhere around 15 billion light-years from Earth in co-moving coordinates, meaning measured in terms of where those objects are located now rather than where they were when their light was emitted. Objects beyond this distance will never be observable no matter how long we wait. This limit is not technological. Building a better telescope would not help. The light from these distant regions simply cannot reach us across expanding space. We could see them if we somehow traveled there faster than light, but relativity forbids that too. These galaxies exist in a part of the universe forever hidden from Earth. The mathematics governing cosmic expansion includes a parameter called the scale factor, which measures how much space has stretched since some reference time. When the universe was half its current age, the scale factor was smaller, meaning distances between objects were shorter. Light traveling toward us from distant galaxies has ridden this expanding scale factor through billions of years, stretching into longer wavelengths as space carried it along. Yet, even with this fundamental understanding, measurements of the expansion rate refuse to agree with each other. Two different methods of measuring cosmic expansion give two different answers. The discrepancy sounds minor at first. One method yields a value near 67 kilometers per second per megaparsec. The other gives roughly 73, just a 9% difference. But that 9% might signal the biggest crisis in cosmology since dark energy was discovered, because both methods appear robust and the disagreement will not go away despite years of scrutiny. The first method uses the cosmic microwave background. We measure the precise pattern of temperature fluctuations across the sky. We input these measurements into our best cosmological model, which includes dark matter, dark energy, and ordinary matter in specific proportions. The model predicts what the expansion rate should be based on how the universe evolved from that early time to now. Answer: 67. The second method uses cosmic distance ladders built from multiple overlapping techniques. We measure the distances to nearby stars using parallax, the apparent shift in position as Earth orbits around our star. We calibrate the brightness of certain variable stars, called Cepheids, using those nearby distances. We find Cepheids in more distant galaxies, where we can also see Type Ia supernovae. We use those supernovae to reach even farther. At the greatest distances, we measure how fast galaxies recede and divide that velocity by the distance to calculate the expansion rate. Answer: 73. Both methods have been refined and checked extensively. The cosmic microwave background measurements from the Planck satellite represent some of the most precise observations in all of physics. The distance ladder method has been improved through decades of work, with better instruments reducing uncertainties at each step. Yet the answers diverge by more than the combined error bars of both measurements. This is not a situation where the numbers overlap within their uncertainties, leaving room for both to be right. The two ranges do not meet. Something is wrong either with the measurements, with our understanding of how the universe evolved between the early time and now, or with fundamental assumptions underlying both methods. If the measurements are both correct, the universe must behave differently than our standard model predicts. Perhaps dark energy evolved over cosmic time instead of remaining constant. Perhaps unseen particles or fields influence the expansion history. Perhaps the assumptions we make about how structure formed or how light travels across space break down under certain conditions. Alternatively, systematic errors might plague one or both methods. Maybe the cosmic microwave background contains subtle features we are misinterpreting. Maybe our distance ladder has a problem at some rung where calibrations go wrong. Maybe dust or other foreground effects contaminate our observations in ways we have not accounted for. Scientists check for these possibilities constantly, but have not found the smoking gun. The tension has grown more severe as measurements improved. Early versions of both methods had large error bars that allowed the numbers to overlap comfortably. But as precision increased, the discrepancy became statistically significant. Now it exceeds 5 sigma in some analyses, meaning if both measurements are correct, the probability of getting such different answers by random chance is less than 1 in a million. Several exotic solutions have been proposed. Maybe the universe expands differently in different directions, violating the cosmological principle that space is homogeneous and isotropic. Maybe we live near the center of a massive void where expansion proceeds faster than average. Maybe new physics operates at specific epochs, changing how structure forms or how light propagates. None of these explanations feel satisfying. All require adding complexity to a model that already works remarkably well for most observations. Scientists generally prefer simpler explanations, following the principle that extraordinary claims require extraordinary evidence. The Hubble tension provides the claim. We are still searching for the evidence that explains it. What drives the expansion that creates this tension remains one of the deepest mysteries in physics. Something invisible permeates every cubic centimeter of space and pushes the universe apart with increasing force. We call it dark energy. We have measured its effects precisely. We know it makes up roughly 68% of the total energy density of the universe. We know it causes cosmic expansion to accelerate rather than slow down. What we do not know is what it actually is or why it exists. The discovery came in the late 1990s from observations of distant supernovae. Type Ia supernovae explode with remarkably consistent brightness, making them excellent distance markers. When astronomers measured how far away these explosions occurred and compared those distances to their redshifts, they expected to find that expansion was slowing over time due to gravitational attraction between galaxies. Instead, they found the opposite. The most distant supernovae appeared dimmer than expected, meaning they were farther away than they should be if expansion was slowing. Something must be accelerating the expansion, pushing space apart against the pull of gravity. The finding was so unexpected that both teams that discovered it spent months checking for errors before announcing their results. Dark energy acts like anti-gravity, but spread uniformly through space rather than concentrated in objects. Unlike normal matter or dark matter, which clump together into galaxies and clusters, dark energy maintains constant density even as space expands. This means, as the universe grows larger, the total amount of dark energy increases proportionally with volume. In the early universe, matter dominated. Its gravity slowed cosmic expansion, though not enough to halt it completely. As space expanded, matter density decreased because a fixed amount of mass spread across increasing volume. Dark energy density remained constant. Eventually, dark energy became more important than matter, and expansion began accelerating. This transition happened about 5 billion years ago. The acceleration has profound consequences. Galaxies already moving apart due to expansion now separate faster with each passing moment. Galaxy clusters that are currently bound together will remain so, held by their mutual gravity. But everything outside our local cluster will eventually disappear from view as space between us and them expands faster than light can travel. One way to understand dark energy involves Einstein's equations of general relativity. The equations allow for a term called the cosmological constant, which represents an energy density inherent to empty space itself. Einstein originally added this term to keep the universe static, fighting against gravitational collapse. When expansion was discovered, he removed it, calling it his biggest blunder. Now it turns out something very much like the cosmological constant appears necessary to explain cosmic acceleration. If dark energy truly is a cosmological constant, it raises troubling questions. Quantum field theory predicts that empty space should contain vacuum energy from virtual particles, constantly appearing and disappearing. When physicists calculate how much vacuum energy should exist, they get a number 10 to the 120th power larger than the observed dark energy density. This is the worst prediction in the history of physics, off by 120 orders of magnitude. Some force or mechanism must cancel almost all the predicted vacuum energy, leaving just the tiny amount we measure as dark energy. No one knows what that mechanism is or why it would cancel so precisely to leave exactly the observed remainder. The coincidence feels too perfect to be accidental. Other theories propose dark energy is not constant but changes over time. Maybe it is a dynamic field that evolves as the universe expands. Maybe it interacts weakly with matter or radiation in ways we have not detected yet. Maybe it represents a modification to gravity itself rather than a new energy component. All we know for certain is that dark energy exists. It dominates the universe now, and it will determine the ultimate fate of everything. Understanding it requires seeing even farther back in time, to the edge of what is physically possible to observe. Light travels at finite speed, which means looking into space always means looking into the past. The farther away an object is, the older the light we receive from it. This gives us a natural time machine for observing cosmic history, but the machine has a hard limit. We cannot see back further than 13.8 billion years because before that moment, the universe was opaque to light. When the cosmos was younger than 380,000 years, temperatures remained too high for neutral atoms to exist. Free electrons scattered photons constantly. Light could not travel more than a tiny distance before bouncing off an electron and changing direction. The universe was like being inside a glowing fog so dense you could not see your hand in front of your face. As the universe expanded and cooled, eventually the temperature dropped below the threshold where electrons could bind to nuclei and form stable atoms. This moment, called recombination, cleared the fog. Photons stopped scattering and began traveling freely through space. The light released at that moment is what we now detect as the cosmic microwave background. Before recombination, the universe was dark to us forever, not because nothing was happening, but because photons could not escape to carry information to distant observers. We cannot see back before that moment using light, no matter how powerful our telescopes become. The cosmic microwave background forms a wall beyond which electromagnetic radiation cannot pass. This creates a spherical shell around us in space-time. The shell marks the surface of last scattering, where the photons we detect today last interacted with matter before beginning their journey toward Earth. Objects that emitted their light before recombination are invisible. Their photons scattered immediately and never began the journey to our telescopes. The shell is not physically located at a specific place in space. Rather, it represents a moment in time visible from every location. An observer in a distant galaxy would see their own cosmic microwave background coming from a different shell centered on their location. These shells overlap throughout space, each observer seeing photons from their own past light cone. Within the 13.8 billion year limit, we can observe cosmic evolution across most of universal history. We see galaxies at different ages, from young and actively forming stars to old and red and nearly dead. We see quasars that were bright in the past, but have since shut down. We see the universe growing and changing, structure assembling, galaxies merging, stars being born and dying. The limit creates urgency for cosmology. Cosmic expansion continually pushes objects toward and beyond our observable horizon. Galaxies visible today will fade from view as expansion carries them too far away for their light to reach us. The window for observing the deep universe gradually closes. Waiting too long means missing phenomena that will become permanently undetectable. Some objects already sit so far away that we see them as they were more than 13 billion years ago, when the universe was less than 1 billion years old. These represent our deepest views into cosmic history. The galaxies and quasars detected at these distances formed during the universe's childhood, mere hundreds of millions of years after the Big Bang. Pushing observations closer to the recombination limit requires increasingly powerful instruments capable of detecting extremely faint and redshifted signals. Each improvement in telescope technology extends our reach slightly further back, but we approach the wall asymptotically. We can get closer, but never reach beyond it using electromagnetic radiation. Other methods might peer even deeper. Gravitational waves travel freely through the universe regardless of its opacity to light. Neutrinos interact so weakly with matter they could have escaped from even earlier epochs. In principle, we could detect signals from the first fractions of a second after the Big Bang using these messengers. For now, 13.8 billion years remains our practical limit for direct observation. Beyond lies a realm we must infer from theory and indirect evidence. Yet, even within this limit, we find regions of space that will never reveal themselves, no matter how long we wait or how sharp our vision becomes. The universe extends far beyond what we can see. Light from distant regions has not had enough time to reach Earth since the Big Bang. These regions exist, containing galaxies and stars and potentially civilizations, but they remain forever invisible to us because their light is still in transit or because cosmic expansion carries them away faster than their light can approach. Imagine the universe as an enormous sphere centered on Earth. The edge of this sphere marks the cosmic horizon. The distance light could have traveled in the 13.8 billion years since photons began moving freely. Everything inside this sphere is potentially observable. Everything outside remains hidden because light from there has not reached us yet. The horizon does not mark the edge of space itself. The universe extends beyond, possibly infinitely. We occupy no special location. An observer in a galaxy 20 billion light-years from Earth would see their own cosmic horizon, centered on their location, revealing regions of space invisible to us, while our observable universe remains hidden from them. This creates a bizarre situation. Vast portions of the universe exist completely disconnected from our possible knowledge. Events happening there now will never be observable from Earth, because by the time light from those events could reach us, cosmic expansion will have carried them beyond our future horizon. They exist in a realm causally separated from us. The separation works both ways. Nothing we do here can influence those distant regions because our signals would need to travel faster than light to reach them before expansion carries them away. We cannot send messages. We cannot exchange information. We cannot detect each other's presence. For all practical purposes, these regions exist in separate universes, despite technically being part of the same space-time. The size of the observable universe continues growing as older light reaches us. Each moment, we see photons that began their journey from slightly farther away. The edge of what we can observe expands outward at light speed. But cosmic expansion simultaneously pushes more distant regions farther away. These two effects compete, with expansion eventually winning for the most distant objects. Dark energy acceleration makes this worse. As expansion accelerates, the cosmic horizon approaches a maximum size beyond which it will not grow. Objects currently near the edge will cross to the far side and disappear from view forever. The observable universe reaches a limit, then begins shrinking as galaxy after galaxy vanishes beyond the receding horizon. Calculate the numbers, and the situation becomes staggering. The observable universe contains roughly 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. The total number of stars visible from Earth exceeds all grains of sand on all beaches on Earth by orders of magnitude. Yet this represents only a tiny fraction of what exists. The full universe extends vastly farther, containing more stars than we can observe by factors we cannot even estimate. Some cosmological models suggest the universe is infinite in extent. If true, then the ratio between the observable universe and the total universe is literally zero. We see an infinitesimal fraction of reality. Most of existence remains hidden, inaccessible, unknowable. Every galaxy we study represents one data point drawn from an infinite sample. This realization should inspire either humility or wonder, possibly both. Everything humans have ever observed, every star we have catalogued, every galaxy we have mapped, every quasar we have detected, represents less than a droplet in an infinite cosmic ocean. The vast majority of reality lies beyond our reach, proceeding through its own evolution independent of our awareness. Even within the observable universe, we face limits on what we can see. Light travels through space, but space itself contains structure that bends and distorts that light in ways that reveal secrets about cosmic architecture, while simultaneously hiding other information forever. Massive objects warp the fabric of space-time around them, creating curves and wells that bend the path of passing light. This effect, predicted by Einstein and confirmed during a solar eclipse in 1919, operates on cosmic scales, where entire galaxy clusters act as gravitational lenses, magnifying and distorting light from objects far behind them. When light from a distant galaxy passes near a massive foreground object, the curvature of space-time around that object deflects the light ray, bending it toward the observer. If the alignment is precise, with the source, lens, and observer positioned along nearly the same line, the light bends enough to create multiple images of the background galaxy. Sometimes these images stretch into arcs or even complete rings surrounding the lensing mass. Galaxy clusters make the most powerful gravitational lenses because they contain enormous quantities of both visible matter and dark matter. The total mass concentration warps space-time significantly enough to produce dramatic lensing effects. Some background galaxies appear stretched into long arcs curving around the cluster center. Others split into multiple, distorted copies appearing at different positions in the sky. These lensed images provide a natural telescope far more powerful than anything humans could build. The gravitational lens magnifies light from the background galaxy, making faint, distant objects visible that would otherwise remain too dim to detect. Astronomers exploit this effect deliberately, targeting known massive clusters and searching behind them for magnified views of extremely distant galaxies. Webb has used gravitational lensing to detect some of the most distant galaxies ever observed. Without the magnification provided by intervening clusters, these galaxies would be completely invisible, their light too faint to register above background noise. The lens boosts their brightness enough to bring them within reach of our instruments. The amount of bending depends on the total mass of the lensing object, including dark matter. By measuring how much background galaxies are distorted and magnified, astronomers can map the distribution of mass in the foreground cluster. This technique reveals dark matter that remains invisible to direct observation. We cannot see dark matter, but we can see how it bends light. These mass maps confirm dark matter makes up the majority of cluster mass. The visible galaxies contribute only a small fraction. Most mass exists as dark matter distributed in an extended halo around the cluster. Sometimes the dark matter and visible matter concentrate in the same regions. Sometimes they separate, particularly in clusters that recently experienced violent collisions, where dark matter passed through while ordinary matter collided and heated. Strong lensing creates multiple distinct images of the same background object. Weak lensing produces subtle shape distortions in many background galaxies that must be measured statistically. Both techniques provide information about foreground mass distribution, but strong lensing offers more dramatic visual examples and allows more precise measurements of extreme magnification. Time delays add another dimension to lensing observations. Light following different paths around the lens travels different distances through curved spacetime. If the background source is variable, like a quasar that brightens and dims, we see those variations occur at different times in the multiple images. Measuring the time delay between images constrains both the mass distribution of the lens and the expansion rate of the universe. Microlensing by individual stars, or compact objects, creates temporary brightening events as the lens passes in front of a background source. These events allow detection of otherwise invisible objects, like rogue planets, brown dwarfs, or even primordial black holes. Continuous monitoring of millions of stars reveals rare alignment events when microlensing occurs. Gravitational lensing operates as a pure consequence of general relativity. The effect depends only on the geometry of curved spacetime, with no need to understand the nature of the mass creating the curvature. This makes it a robust tool for studying dark matter and measuring cosmic distances. Yet even with this powerful technique, revealing hidden mass and magnifying distant objects, we cannot see everything. Time itself behaves strangely at cosmic distances in ways that further complicate our observations of the deep universe. Events in distant galaxies unfold in slow motion from our perspective, stretched by the expansion of space itself. A supernova that explodes in a fraction of a second at its location appears to brighten and fade over weeks or months when we observe it from billions of light years away. The universe dilates time across cosmic distances, making ancient history play out like a movie running at reduced speed. This stretching comes from the same expansion that redshifts light. As space grows between the distant galaxy and Earth, each successive wavefront of light must travel slightly farther than the one before it. Photons emitted 1 second apart at the source arrive more than 1 second apart at our detectors. The gap increases proportionally with distance. For galaxies billions of light years away, time dilation factors reach 2, 3, even 5 times normal. A star that burns for 1 million years in its own reference frame appears to shine for 5 million years when observed from Earth if time dilation factor equals 5. Nuclear reactions in the stellar core proceed at their normal rate locally, but from our distant viewpoint, everything happens in extended slow motion. Supernovae provide the clearest demonstration. Type Ia supernovae follow a characteristic light curve, brightening rapidly to peak luminosity, then fading over the following weeks. When astronomers observe these explosions in nearby galaxies, the light curves match predictions exactly. When they observe the same type of explosion in distant galaxies, the light curves stretch proportionally with redshift. A supernova at redshift 1, where light has been stretched to twice its original wavelength, takes twice as long to brighten and fade. A supernova at redshift 2 takes 3 times longer. The relationship holds precisely, providing independent confirmation that cosmic expansion affects time, as well as space. Physics operating in distant galaxies follows the same laws, but the expanding universe distorts our view of their timescales. This creates strange situations. When we observe a galaxy 10 billion light-years away, we see it as it existed 10 billion years ago. But we also see its internal processes running slowly compared to local time. A year of activity in that galaxy stretches to several years in our observations. The galaxy lives through its evolution at normal speed, in its own frame of reference, while appearing to move through time more leisurely from ours. Time dilation affects everything we measure about distant objects. Rotation rates of galaxies appear slower. Orbital periods of binary stars take longer. Variable stars pulse with extended periods. Even the expansion of supernova remnants happens at apparently reduced speeds. Any process that involves change over time gets stretched by the expanding space between observer and observed. The effect compounds with distance. The most distant galaxies we observe exist at redshifts approaching 10 or higher, meaning their light has been stretched to more than 10 times its original wavelength. Time dilation at these distances reaches factors of 11 or more. A billion years of evolution in the galaxy's reference frame spans 11 billion years in our stretched view of their history. This asymmetry reveals the relativity of time itself. There exists no universal clock ticking at the same rate everywhere. Time flows differently depending on your reference frame, your motion through space, and the gravitational field you occupy. Cosmic expansion adds another layer, where time rates depend on the distance light must travel through expanding space to reach you. Understanding time dilation becomes essential for reconstructing the actual history of distant objects. When we see a galaxy forming stars at a certain rate, we must correct for time dilation to determine the true star formation rate in the galaxy's own time frame. The corrections grow larger for more distant observations, affecting our understanding of how quickly the early universe assembled its structures. Yet, even accounting for time dilation, the early universe produced structures that defy expectations. The first stars that ignited were nothing like the ones shining today. They were monsters operating under conditions that no longer exist anywhere in the modern cosmos. The universe's first stars were titans that dwarfed anything burning today. These population 3 stars contained masses reaching 200, 300, even 500 times what our own star weighs. They burned with ferocious intensity, consuming their nuclear fuel in mere millions of years instead of the billions our star will take. They shone with the light of several million smaller stars, compressed into single points. These monsters could only form under the pristine conditions of the infant universe. After the Big Bang, only hydrogen and helium existed in significant quantities. No heavy elements polluted the gas clouds from which stars formed. This absence of metals, as astronomers call all elements heavier than helium, changed everything about how stars could form. In the modern universe, heavy elements act as coolants in collapsing gas clouds. When a cloud contracts under gravity, compression heats the gas. Carbon and oxygen atoms radiate away this heat efficiently through collisions and electromagnetic emission. The cloud cools even as it collapses, allowing more material to fall inward before heat pressure stops the contraction. This cooling process limits the final mass of forming stars. Primordial gas lacked these cooling agents. Hydrogen and helium cool much less efficiently. When primordial clouds collapsed, they heated rapidly and could not shed that heat as effectively. The rising temperature created pressure that fought against further collapse. Only the most massive clouds had enough gravitational force to overcome this pressure and continue contracting. The result was stars hundreds of times more massive than typical modern stars. These giants lived fast and died young. Nuclear fusion in their cores proceeded at tremendous rates, burning through hydrogen supplies in just a few million years. The most massive ones might have survived only 1 or 2 million years total. For comparison, our star has been burning for 4.5 billion years and will continue for another 5 billion at least. The surface temperatures of population 3 stars reached over 100,000 degrees, more than 15 times hotter than our star's surface. They radiated most of their energy as ultraviolet light, invisible to human eyes but devastating to anything nearby. A single population 3 star could sterilize entire regions of space around it with intense radiation. Their interiors operated under extreme conditions. Core temperatures climbed to hundreds of millions of degrees. Densities reached levels where matter behaved in exotic ways. Nuclear reactions proceeded through different pathways than those operating in modern stars, producing unusual ratios of elements. The physics at these extremes pushed to the boundaries of what stellar theory can model. Some population 3 stars might have been so massive they bypassed the normal supernova death and collapsed directly into black holes. Above a certain mass threshold, The iron core grows so large that when fusion stops and gravity takes over, nothing can halt the collapse. The entire star implodes into a black hole in seconds, releasing minimal energy to the outside universe. These direct collapse events could have seeded the early universe with black holes ready to grow into the supermassive monsters we find in ancient galaxies. Others exploded as pair instability supernovae, among the most violent stellar deaths possible. In these events, gamma rays in the core become energetic enough to spontaneously create electron-positron pairs. This sudden energy loss removes pressure support. The core collapses catastrophically. The rebound blows the entire star apart with such force that no remnant remains. The star obliterates itself completely, dispersing all its material into surrounding space. The violence of these first stellar deaths played a crucial role in cosmic chemical enrichment. The explosions scattered newly created elements across vast distances, polluting pristine hydrogen and helium with the first metals. This contamination changed the conditions for the next generation of star formation, leading to smaller stars more similar to those we see today. But the first stars had to form first, and their composition tells us about the untouched materials that emerged from the Big Bang. Population 3 stars contain nothing heavier than lithium, no carbon, no oxygen, no iron, no silicon, none of the elements that make up planets, life, or most of the matter we interact with daily. Just hydrogen, helium, and trace amounts of lithium created in the Big Bang itself. This chemical purity made them fundamentally different from every star burning in the modern universe. When astronomers classify stars by composition, they use the term metallicity. High metallicity means lots of heavy elements. Low metallicity means few. Zero metallicity means none at all, except for the tiny amounts of lithium that formed during primordial nucleosynthesis. Population 3 stars represent this theoretical 0 point, though we have never directly observed one. The absence of metals affected everything about these stars. Their opacity, the way light interacted with their material, differed from modern stars. Radiation could escape more easily from deep within their interiors because fewer heavy elements blocked the photons through absorption. This changed the balance between radiation pressure pushing outward and gravity pulling inward. Their spectra would have shown only hydrogen and helium lines if we could observe them. No absorption features from carbon, nitrogen, oxygen, or iron. No molecular bands from compounds that require heavier elements to form. Just the simplest possible stellar atmosphere displaying the simplest possible chemistry. Spectroscopy of these stars would reveal the universe in its most primitive chemical state. Finding a surviving population 3 star would revolutionize astronomy. We could study the physics of metal-free stellar evolution directly, instead of relying on computer models. We could test theories about how nuclear reactions proceed in pure hydrogen-helium environments. We could observe the exact conditions that existed before stellar nucleosynthesis enriched the cosmos. The problem is, these stars no longer exist. They all died billions of years ago, exhausting their fuel and exploding or collapsing within a few million years of formation. Their remnants might persist as black holes or neutron stars, but the stars themselves vanished from the universe before most modern galaxies finished forming. We missed them by arriving too late. Some astronomers search for extremely low metallicity stars that might represent the second generation, stars that formed from gas, slightly enriched by the very first population 3 supernovae. These stars would contain tiny amounts of heavy elements, just enough to change their formation process while preserving clues about the composition of their parent clouds. A few candidates have been identified, ancient stars with metal content less than 1/millionth that of our star. Studying these second-generation stars provides indirect evidence about population 3 stars. The pattern of elements present in extremely metal-poor stars reflects the types of supernovae that enriched their birth clouds. Different explosion mechanisms produce different element ratios. By measuring these ratios, astronomers can infer what kinds of explosions occurred, which tells them about the masses and fates of the stars that exploded. One surprise from these studies is that some extremely metal-poor stars show enhancement of certain elements, like carbon or nitrogen relative to iron. This suggests the first supernovae did not distribute elements uniformly. Different explosion types produce different chemical signatures. Some early stars might have ejected mostly lighter elements. Others might have created more iron peak elements. The diversity hints at a complex early stellar population rather than identical giants. The zero metallicity composition also meant population 3 stars could not form planetary systems like ours. Planets require rocky materials and ices to build solid bodies. Rocky materials need silicon, iron, magnesium. Ices need oxygen, carbon, nitrogen. Without these elements, planets cannot condense from the protostellar disk. Population 3 stars might have had gas giant planets made of hydrogen and helium, but no rocky worlds, no asteroid belts, no possibility of Earth-like environments. Life, as we understand it, requires chemistry involving carbon, nitrogen, oxygen, phosphorus, and other heavy elements. Population 3 stars provided none of these building blocks. Their planetary systems, if any formed, would be completely sterile, devoid of the materials needed for complex chemistry. Life had to wait for later generations of stars to create and distribute the necessary elements. When these massive stars died, they changed the universe forever by introducing the first heavy elements into existence. The explosions that ended their brief lives seeded space with the raw materials from which everything else would eventually form. The deaths of population 3 stars transformed the cosmos from chemically simple to complex. When these giants exploded, nuclear reactions in the shock waves synthesized elements that never existed before. Carbon, oxygen, silicon, iron, gold, uranium appeared for the first time, created in seconds during the most violent events in nature. The explosions scattered these newly forged elements across millions of light years, mixing them into the primordial hydrogen and helium. Inside stars, nuclear fusion builds heavier elements from lighter ones. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Carbon and oxygen fuse into neon, magnesium, silicon. Silicon fuses into iron. Each step releases energy that supports the star against gravitational collapse. But fusion beyond iron consumes energy instead of releasing it. No ordinary stellar process creates elements heavier than iron through fusion. Supernovae change the rules. The tremendous energies available during stellar explosions drive reactions that would never occur under normal conditions. Neutrons flood the environment, slamming into existing nuclei and getting absorbed. Nuclei capture multiple neutrons in rapid succession, building up to heavier and heavier elements before they have time to decay. This rapid neutron capture process, called the R process, creates roughly half of all elements heavier than iron. Gold forms this way. Platinum, uranium, thorium, all the elements that make certain rocks radioactive, all the elements used in nuclear reactors and weapons, they all require neutron capture in extreme environments to exist. Every gold atom in every ring, every coin, every electronic device was created either in a supernova explosion or in the collision of 2 neutron stars. There is no other way to make gold in the universe. Population 3 supernovae injected the first doses of these heavy elements into the surrounding gas. The explosions created blast waves that swept up material across vast distances, mixing the enriched ejecta with pristine gas. Gradually, the average metallicity of the universe increased from 0 to small but measurable values. This contamination was not pollution but enrichment, adding the chemical diversity needed for complexity. Second-generation stars formed from this enriched gas. They still consisted mostly of hydrogen and helium, but now contained trace amounts of carbon, oxygen, iron, and other elements. This small addition changed their formation process, their internal structure, their lifetimes. These stars could form at lower masses than population 3 stars. because the heavy elements improved cooling efficiency. Smaller stars formed, stars more like our own, stars that would burn for billions or even trillions of years instead of just millions. Rocky planets became possible. Dust grains made of silicon, iron, and oxygen condensed in the cooling ejecta from supernovae and in the disks around new stars. These grains stuck together through collisions, building up into pebbles, boulders, asteroids, eventually planets. The earth beneath your feet, the silicon in computer chips, the iron in blood, all originated in stellar explosions billions of years ago. Organic chemistry became possible. Carbon atoms could bond with hydrogen, oxygen, nitrogen to form complex molecules. Amino acids, sugars, lipids, the building blocks of life, all require carbon and other heavy elements. Without supernova enrichment, none of these molecules could exist. Life itself depends on violent stellar deaths that occurred in the distant past. Each generation of stars further enriched the universe. Stars formed from enriched gas, burned through their lifetimes, exploded, added more heavy elements to the mix. The cycle repeated billions of times across cosmic history. The metallicity of the universe gradually increased from nearly zero in the beginning to the roughly 2% heavy element content we measure today. Our star formed from gas that had been cycled through multiple generations of stars. The heavy elements it contains represent the accumulated debris from countless supernovae that exploded over billions of years. We are literally made of stardust, assembled from elements created in stellar furnaces and scattered by cosmic violence. But between the death of the first stars and the formation of the next generation, the universe entered a period of darkness that lasted far longer than the brief era when population the three stars burned. The cosmos went dark for hundreds of millions of years while gravity slowly assembled the structures that would become the next wave of star formation. After the first stars died, the universe went dark. No new stars ignited immediately to replace them. The explosions dispersed material across vast distances. Gas needed time to cool, to clump together again under gravity, to reach densities high enough for fusion. For hundreds of millions of years, space sat in near total darkness, lit only by the fading cosmic microwave background radiation gradually cooling toward invisibility. Astronomers call this period the Cosmic Dark Ages. It stretched from roughly 10 million years after the Big Bang, when the last population 3 stars exploded, until around 400 million years after the Big Bang, when the next generation of stars began igniting in sufficient numbers to illuminate space. During this enormous span, matter moved silently under gravity's influence, building structures that remained invisible. Dark matter continued its work throughout the Dark Ages. Unaffected by the lack of light, dark matter halos grew through gravitational attraction. Small halos merged into larger ones. Filaments formed, connecting regions of higher density. The cosmic web took shape in darkness, creating the gravitational scaffolding upon which visible structures would later build. Ordinary matter fell into the dark matter wells, hydrogen and helium gas, now enriched with trace amounts of heavy elements from population 3 supernovae, gradually accumulated in the densest regions. The gas collisions generated heat, but the heavy elements allowed efficient cooling. Slowly, conditions developed that would trigger the next era of star formation. Imagine the universe during this time. Total silence, total darkness, except for the dim glow of increasingly redshifted microwave radiation. No stars twinkled, no galaxies shone, no quasars blazed across space. Just cold hydrogen gas drifting through voids and accumulating along filaments, following invisible dark matter flows toward gravitational centers. The temperature of the universe dropped steadily during the Dark Ages. At recombination, when the cosmic microwave background formed, temperatures hovered around 3,000 degrees. By the time the Dark Ages ended, temperatures had fallen to a few dozen degrees above absolute zero. The expanding universe carried heat away, through the stretching of space itself, cooling everything uniformly. Gas chemistry during the Dark Ages proceeded through simple reactions. Hydrogen atoms occasionally collided and formed molecular hydrogen. Two atoms bonded together. These molecules became the main coolant, allowing gas clouds to collapse. When molecular hydrogen collides with other atoms, it can radiate away energy efficiently, allowing the cloud to compress further. Without molecular hydrogen, the first generation of post-population 3 stars might never have formed. Dark matter halos reached masses where they could retain gas against the dispersive effects of early supernova explosions. Smaller halos lost their gas entirely when nearby population 3 stars exploded. The blast waves swept through these low-mass halos, heating the gas above escape velocity and blowing it out into intergalactic space. Only halos, massive enough to have deep gravitational wells, could hold onto gas and eventually form stars. The Dark Ages ended gradually rather than suddenly. Stars began igniting in scattered locations when local conditions reached the necessary thresholds. These second-generation stars, smaller and longer-lived than population 3 stars, accumulated slowly. At first, they barely disturbed the darkness. But over millions of years, their numbers increased. More stars meant more light. More light meant more heating of surrounding gas. More heating meant ionization started spreading. The transition from Dark Ages to the epoch of reionization marked a fundamental change in cosmic history. The universe transformed from neutral to ionized, from dark to illuminated, from simple to complex. This transformation happened because the accumulated light from billions of young stars grew intense enough to strip electrons from hydrogen atoms across vast volumes of space. What came next rewrote the chemistry of the universe. Ultraviolet radiation from billions of young stars tore electrons away from hydrogen atoms across the entire cosmos. This process, called reionization, converted the neutral hydrogen gas filling space back into plasma, reversing the recombination that occurred 380,000 years after the Big Bang. The universe became transparent to ultraviolet light, allowing radiation to travel freely across cosmic distances and fundamentally changing how structures could form. Neutral hydrogen absorbs ultraviolet photons efficiently. When ultraviolet light hits a neutral hydrogen atom, it can kick the electron completely free, ionizing the atom. In the Dark Ages, the universe contained mostly neutral hydrogen. Any ultraviolet sources that briefly appeared found their radiation quickly absorbed by surrounding gas, limiting how far the light could propagate. As star formation accelerated, the cumulative ultraviolet output increased. Each young massive star produced vast quantities of ultraviolet photons. These photons ionized hydrogen in the star's immediate vicinity, creating bubbles of ionized gas around individual stars and star clusters. Initially, these bubbles remained small and isolated, surrounded by vast oceans of neutral hydrogen. The bubbles grew as stars continued pumping out ultraviolet radiation. When two expanding bubbles met, they merged into larger ionized regions. More stars meant more bubbles. More bubbles meant faster merging. The process accelerated as ionized regions began connecting across cosmic distances. Eventually, the ionized bubbles filled most of space, leaving only isolated pockets of neutral hydrogen. Quasars contributed substantially to reionization. The supermassive black holes powering these brilliant objects emitted enormous amounts of ultraviolet radiation, far more than entire galaxies of normal stars. A single bright quasar could ionize a sphere of gas hundreds of millions of light-years across. The most luminous quasars created cosmic-scale ionization zones, carving out enormous bubbles in the neutral hydrogen sea. Reionization took time. The process began around 400 million years after the Big Bang and continued for several hundred million years more. Different regions reionized at different times depending on local star formation rates and the presence of nearby quasars. Some areas transformed early, others remained neutral longer, finally getting ionized by radiation from surrounding regions. We can study reionization by observing very distant quasars. Light from these objects passes through whatever gas lies between the quasar and Earth. Neutral hydrogen along the path absorbs specific wavelengths, creating absorption features in the quasar's spectrum. By measuring how much absorption occurs at different wavelengths, astronomers map the distribution of neutral versus ionized hydrogen at different cosmic epochs. The Gunn-Peterson trough appears in spectra of the most distant quasars. Below a certain wavelength, the spectrum shows almost complete absorption, indicating the light traveled through significant neutral hydrogen before reaching us. This trough marks the transition between fully ionized intergalactic medium nearby and partially neutral medium in the early universe. The trough's location varies between different quasars depending on their distance, revealing how reionization progressed. Reionization heated the intergalactic medium substantially. Ionization imparts kinetic energy to freed electrons. These electrons collide with other particles, sharing energy and raising the overall temperature. The medium heated from tens of degrees to tens of thousands of degrees. This heating suppressed star formation in low-mass halos because the increased pressure prevented gas from cooling and collapsing efficiently. The chemistry of the universe changed permanently. Neutral hydrogen can form molecules and dust. Ionized hydrogen cannot. Reionization prevented complex chemistry from occurring in intergalactic space, confining molecule formation to dense regions inside galaxies, where self-shielding could protect gas from ionizing radiation. This shaped where planets could form and where life might eventually emerge. The process continues today at lower levels. Stars and quasars constantly ionize surrounding gas, maintaining the ionized state of the intergalactic medium. Without this continued input of ionizing radiation, electrons would eventually recombine with protons, returning the universe to a neutral state. Reionization was not a one-time event, but an ongoing process sustained by continuous star formation. Yet despite reionization making the universe transparent again, we find ancient galaxies that should not exist according to our models of how fast this process allows structures to form. The timeline keeps compressing in ways that challenge fundamental assumptions. The ancient galaxies Webb detected assembled far too quickly according to standard models. Current theories predict a gradual hierarchical process where small structures merge into larger ones over billions of years. Yet we see massive organized galaxies less than 500 million years after the Big Bang. Something accelerated structure formation beyond what gravity alone should accomplish in the available time. Cosmologists built their models on solid foundations. Dark matter collapses into halos following gravitational physics. Gas falls into those halos and cools. Stars form when gas reaches sufficient density. Galaxies grow through mergers and accretion. Each step takes time governed by fundamental physical processes. The models reproduce modern galaxy populations accurately, matching observations of nearby structures. The models also successfully predict how structures should have looked at intermediate times. Observations of galaxies at moderate distances, where light left several billion years ago, match predictions well. Galaxy masses, sizes, colors, and morphologies all agree with simulated galaxies at corresponding epochs. The models work for most of cosmic history, but when pushed back to the earliest times, the models fail. They predict that at 500 million years after the Big Bang, the largest galaxies should contain perhaps a few hundred million stellar masses, still small and actively assembling. Instead, Webb finds galaxies with billions of stellar masses already in place, displaying mature characteristics, suggesting longer evolutionary timescales than the universe had provided. Several explanations compete for acceptance. Perhaps dark matter behaves differently than assumed. Maybe it interacts with itself or with ordinary matter through forces beyond gravity, allowing faster collapse. Maybe dark matter particles decay or annihilate, releasing energy that influences structure formation. These scenarios require new physics beyond the standard model of particle physics and cosmology. Alternatively, the initial density fluctuations might have been larger than measured in the cosmic microwave background. If certain regions started with enhanced density, structures there could form faster. But this creates tension with cosmic microwave background observations that constrain fluctuation amplitudes precisely. Reconciling large fluctuations locally with small fluctuations globally requires special conditions. Another possibility involves feedback processes working differently in the early universe. Supernovae and quasars inject energy into their surroundings, which can either suppress or stimulate star formation depending on conditions. Perhaps in the dense environment of the infant cosmos, feedback triggered rapid star formation instead of shutting it down. Compression from nearby explosions might have caused gas clouds to collapse faster. Direct collapse of massive gas clouds could bypass normal hierarchical assembly. If conditions allowed entire galactic masses of gas to fall inward simultaneously, galaxies might form in single catastrophic events rather than through gradual accumulation. This requires specific thermal conditions where gas can collapse without fragmenting into individual stars first, maintaining coherence across enormous masses. Some theorists propose modifications to gravity itself. Einstein's general relativity works perfectly for solar system scales and has passed every test in the modern universe. But perhaps at the extreme densities and scales of the early universe, gravity operated slightly differently. Small changes to gravitational physics could significantly accelerate structure formation without violating any observations in the present-day cosmos. Each proposed solution faces challenges. Dark matter modifications must explain why the same physics does not affect modern structure formation. Enhanced density fluctuations must remain invisible in cosmic microwave background data. Alternative feedback mechanisms need specific conditions that may not have existed. Direct collapse requires fine-tuned thermodynamics. Modified gravity must predict all current observations while changing only early behavior. The tension between models and observations suggests our understanding remains incomplete. Either we are missing crucial physics, or we are misinterpreting the observations, or our estimates of cosmic ages and distances contain systematic errors. Resolving this mystery requires both better observations and deeper theoretical work. Meanwhile, measurements of cosmic distances keep pushing back the records for earliest observed objects. The continual discovery of increasingly distant structures forces us to confront how far we can actually see into the universe's past. Astronomers measure cosmic distances using redshift, the stretching of light caused by cosmic expansion. The farther away an object sits, the more space has expanded during the light's journey. The more the light waves stretched, the higher the redshift. Each new generation of telescopes pushes observations to higher redshifts, revealing structures from earlier cosmic epochs and breaking previous distance records with increasing frequency. Redshift quantifies how much wavelengths have stretched. A redshift of 1 means wavelengths doubled. Redshift 2 means they tripled. The relationship between redshift and distance is not linear because expansion rate changed throughout cosmic history. Converting redshift to distance or age requires assumptions about dark matter, dark energy, and the overall geometry of the universe. Ground-based telescopes reached redshifts around 7 for galaxies, corresponding to roughly 750 million years after the Big Bang. The atmosphere blocks infrared light beyond certain wavelengths, limiting observations of the most distant objects whose visible light has been redshifted into infrared wavelengths. Breaking past redshift 7 required space telescopes. Hubble Space Telescope extended observations to redshift 11, pushing back to galaxies existing just 400 million years after the Big Bang. These detections required gravitational lensing to magnify faint, distant sources enough to detect them above background noise. The observations revealed surprisingly luminous and massive galaxies at epochs when theory predicted mostly small, faint objects. Webb shattered previous records, within months of beginning science operations. Candidate galaxies at redshift 13, 14, even higher appeared in early data. Some candidates showed photometric redshifts, suggesting they existed less than 300 million years after the Big Bang. If confirmed through spectroscopy, these objects would push observations to the earliest moments when galaxies could possibly exist. Spectroscopic confirmation provides certainty that photometric estimates cannot match. Photometry measures brightness in several broad wavelength bands, allowing rough redshift estimates based on the overall color and brightness pattern. Spectroscopy spreads light into its component wavelengths, revealing detailed features that pin down redshift precisely. Many photometric candidates await spectroscopic follow-up to confirm their extreme distances. Each confirmed high redshift galaxy teaches us about the early universe. The galaxy's brightness reveals star formation rate. Its color indicates stellar population age. Spectral lines show chemical composition. Morphology suggests dynamical state. Every data point constrains models of how the first galaxies assembled and evolved. The current record holders sit at redshifts above 13, corresponding to times less than 350 million years after the Big Bang. These galaxies appear remarkably bright despite their youth. They contain billions of stellar masses already. They show evidence of active star formation, producing hundreds of solar masses in new stars per year. All of this occurs in a universe barely 3% of its current age. Discovering galaxies at progressively higher redshifts demonstrates the power of infrared observations. Visible light from these distant sources gets redshifted into near-infrared and mid-infrared wavelengths. Webb's Large Mirror and sensitive infrared instruments can detect photons that left these galaxies when the universe was in its infancy, photons that have traveled through expanding space for over 13 billion years. The records will continue falling. Webb will operate for years, potentially decades. Each observing program targets different fields of sky, different wavelength ranges, different integration times. More data means more rare distant galaxies discovered. Future space telescopes with even larger mirrors or more sensitive instruments will push observations to even higher redshifts. There exists a theoretical maximum redshift around 30 for the first galaxies, and perhaps 1000 for the cosmic microwave background itself. Beyond redshift 1000, we reach the epoch of recombination when the universe became transparent. No structures existed before that moment, only smooth, expanding plasma. The ultimate distance limit lies there, marking the edge beyond which electromagnetic observations cannot penetrate. But even within observable limits, we encounter phenomena that challenge our understanding of cosmic causality. Some galaxies appear to behave in ways that suggest time itself flows backwards at the edges of reality. Observing distant galaxies creates paradoxes that twist our understanding of cosmic evolution. We see these objects as they were billions of years ago, frozen in ancient configurations. Meanwhile, in their own reference frame, they have evolved dramatically, possibly merged with neighbors, possibly died entirely. The galaxy we observe no longer exists in that form anywhere in the universe. We study phantoms from the past. This temporal disconnect becomes extreme at the highest redshifts. A galaxy at redshift 10 appears as it existed just 500 million years after the Big Bang. That light began traveling toward us over 13 billion years ago. During those 13 billion years of travel time, the galaxy continued evolving in its own local time. It formed new stars, expelled gas through winds, accreted material from surroundings, perhaps collided with neighbors. Today, that same galaxy exists in a completely different state than what we observe. It might have grown into a massive elliptical galaxy, its star formation long since shut down, its population ancient and red. Or it might have merged with other galaxies, its identity dissolved into a larger structure. Or it might have been disrupted entirely, its stars scattered across a cluster. We have no way to know without traveling there at faster than light speeds. The light we detect provides information about the past, not the present. When we measure the galaxy's properties, we measure how it was, not how it is. We cannot update our observations to account for 13 billion years of subsequent evolution because no information from that evolution has had time to reach us. We remain causally disconnected from the galaxy's current state. This creates odd situations when we observe multiple galaxies at different distances. A galaxy at redshift 1 shows us that object's configuration 7 to 8 billion years ago. A galaxy at redshift 5 shows us its state 11 to 12 billion years ago. If these galaxies eventually merge, we might be seeing the two components separately, even though in the present moment they have already combined into a single system. We observe the past of objects whose futures have already happened elsewhere in space. The expansion of space compounds the strangeness. While light travels toward us, space expands, carrying the emitting galaxy farther away. The galaxy is now much more distant than 13 billion light-years, even though the light took 13 billion years to arrive. Its current distance exceeds 30 billion light-years due to the expansion that occurred during the light travel time. It recedes faster than light speed. If we could instantaneously teleport to the galaxy's current location, we would find it in a completely different state than we observe from Earth. Stars that appear young and blue in our telescopes would have long since evolved and died. Star-forming regions we detect would have exhausted their gas supplies billions of years ago. The galaxy's morphology, color, and spectral features would bear little resemblance to what we measure. Yet we can never access the galaxy's current state through observation. Light leaving it today will take billions of years to reach us, arriving when Earth and our star may no longer exist. The present state of that galaxy exists forever beyond our observational horizon, knowable only through inference and modeling. We must reconstruct what happened to it using simulations and theories rather than direct measurements. This asymmetry between past observations and present reality affects how we interpret data. When we count galaxies at different redshifts to measure cosmic star formation history, we are literally watching the same objects at different ages. A single galaxy might appear in multiple redshift bins if we observe it at different distances, seeing its evolution across cosmic time. Accounting for this requires careful statistical modeling. Cosmic look-back time means we observe the universe not as it is, but as it was, with the timeline varying by distance. The farthest objects reveal the earliest moments. Nearby objects show recent cosmic history. Piecing together the full story requires combining observations across all distances into a coherent narrative of evolution from past to present. And that full story reveals something troubling about physics at the absolute edge. At the extreme distances Webb observes, our physical models begin failing. The assumptions underlying cosmology, tested and validated for nearby and intermediate distance observations, might not hold in the radically different conditions of the infant universe. Density was higher. Temperatures were extreme. Quantum effects possibly influenced macroscopic structures. The rules governing how matter behaves might have operated differently. General relativity describes gravity accurately in the solar system, across galaxy clusters, and throughout the modern universe. But in the extreme space-time curvature near black holes, or during the first moments after the Big Bang, quantum effects become important. We lack a theory of quantum gravity that seamlessly combines general relativity with quantum mechanics. This gap in understanding affects our ability to model the earliest cosmic epochs. The Big Bang singularity itself represents a breakdown of physics. Rewinding cosmic expansion backwards in time, density, and temperature increase without limit. At some point, before reaching zero time, our equations produce infinite values. Infinities in physics usually signal that the theory has reached its limits. Something must replace general relativity at these extreme conditions. Some quantum theory of gravity we have not yet discovered. Inflation, the hypothesis that the universe underwent exponential expansion in its first fraction of a second, was proposed specifically to solve problems arising from extrapolating the Big Bang backwards. Without inflation, the universe should have been much lumpier, with vastly different temperatures in different regions depending on their causal history. Inflation smooths out these variations by stretching a tiny causally connected region to cosmic scales. But inflation itself requires exotic physics, a scalar field with unusual properties not seen anywhere in the modern universe. Dark energy presents similar issues. The cosmological constant in Einstein's equations provides a simple mathematical description of accelerating expansion. But the physical origin of this constant remains unknown. Why does empty space have an energy density? Why does that density take the specific value we measure rather than being enormously larger or exactly zero? These questions have no answer in current physics. Dark matter avoids detection despite comprising most of the matter in the universe. Every attempt to directly observe dark matter particles has failed. We know something is there through gravitational effects, but we do not know what it is. It might be a new type of fundamental particle. It might be primordial black holes. It might be modifications to gravity rather than new matter. Each possibility requires extending physics beyond the standard model. The first moments after the Big Bang involved energies far beyond anything achievable in particle accelerators. At these energies, particles we have never observed existed in equilibrium. Forces that appear separate today might have been unified. The laws of physics as we know them might have been different. Testing theories about these extreme conditions requires observations of their remnant effects on cosmic structure. Fine-tuning problems plague cosmology. Many physical constants appear precisely calibrated to allow complex structures to form. If the cosmological constant were much larger, space would have expanded too fast for galaxies to assemble. If nuclear forces were slightly different, stable atoms might not exist. The universe seems optimized for our existence, which either reflects an anthropic selection effect or hints at deeper principles we do not understand. Observations of the earliest galaxies might reveal where our models break down. If galaxies systematically appear more massive, more mature, or more abundant than predictions, it signals missing physics. Either we misunderstand how structure forms, or the early universe operated under different rules, or our entire cosmological framework requires revision. The discrepancies Webb observes suggest at least one of these possibilities might be correct. Quantum fluctuations during inflation created the seeds of all structure. These fluctuations occurred at such tiny scales and early times that quantum mechanics and gravity necessarily intertwined. Understanding how this happened requires quantum gravity, the missing piece in our theoretical framework. Without it, we cannot fully explain why galaxies exist or why they have the properties we observe. At the absolute edge of observability, where physics becomes uncertain and observations become difficult, we must confront uncomfortable truths about the limits of knowledge. And among those truths is the recognition that our window to observe deep cosmic history is slowly closing as the universe continues expanding. The universe's accelerating expansion will eventually erase most galaxies from view. Objects currently visible will recede beyond the cosmic horizon, their light no longer able to reach us across the growing gap of expanding space. Trillions of years from now, observers in our galaxy will see a much emptier cosmos, with only our local cluster of gravitationally bound galaxies remaining observable, while the rest of the universe vanishes into unreachable darkness. Dark energy drives this cosmic isolation. Its repulsive effect grows stronger as space expands, creating more volume for dark energy to occupy. While gravity binds matter into galaxies and clusters locally, on larger scales, dark energy dominates. It pushes galaxy clusters apart from each other with increasing force. Eventually, the recession velocity of distant clusters exceeds light speed, placing them beyond observation forever. The process has already begun. Galaxies at the edge of the observable universe already recede faster than light. We see them only because we detect photons they emitted billions of years ago, when they were closer and receding more slowly. But galaxies currently near the boundary continue falling behind the cosmic horizon. Their newest light will never reach us because space expands too quickly in between. Calculate the future, and the picture grows stark. Objects now at moderate distances will eventually cross the horizon. A galaxy currently 10 billion light-years away might remain visible for another few tens of billions of years before its recession velocity exceeds light speed. Once across that threshold, it vanishes. We lose the ability to observe it, communicate with it, or influence it in any way. It exits our universe for all practical purposes. The local group of galaxies, including the Milky Way, Andromeda, and several dozen smaller galaxies, will remain bound together. Gravity within this cluster exceeds the expansive push of dark energy. These galaxies will eventually merge into a single large elliptical galaxy. This combined system will be all that observers billions of years from now can see, unless they developed astronomy early enough to record observations of the currently visible universe. Imagine the view from Earth a trillion years from now. The night sky shows one giant galaxy, the merger product of the local group. Beyond that, total darkness, no distant galaxies, no cosmic microwave background, which will have redshifted into undetectably long wavelengths, no quasars, no supernovae in external galaxies. The universe will appear to consist of a single galaxy surrounded by empty space. Future civilizations arising in this isolated galaxy would have no evidence that a larger universe exists beyond their cosmic shores. They would observe stellar motions, study star formation, map their galaxy structure, but they would lack any hint that billions of other galaxies once filled the cosmos. The expansion of space will have erased the evidence. This creates a disturbing implication. Information about the universe's true nature gets progressively hidden as expansion continues. We happen to live at an epoch when distant galaxies remain visible, when the cosmic microwave background can still be detected, when evidence of the Big Bang and cosmic evolution remains accessible. Future epochs will not be so fortunate. The fading of cosmic evidence challenges the principle that physical laws remain constant and observable throughout time. Yes, the laws stay the same, but the evidence supporting our understanding of those laws gradually disappears. What if we lived much later in cosmic history? Would we discover dark energy? Would we know about the Big Bang? Would we realize the universe had a beginning and is expanding? Perhaps we ourselves have already lost evidence of physics that operated in the early universe. Perhaps signatures of quantum gravity or exotic inflation mechanisms, or the nature of dark matter, existed in observational data available during earlier epochs, but have since faded beyond detection. We might be missing crucial information simply because we arrived too late to observe it. The accelerating loss of observable galaxies reminds us that the universe does not preserve information indefinitely. Expansion carries evidence away. Redshift diminishes signals. Entropy increases. The cosmos becomes increasingly difficult to study as time passes. Our current era represents a privileged time for cosmology. Humanity exists during a brief window when deep cosmic observations remain possible. Billions of years from now, dark energy will have pushed most of the universe beyond detection. Billions of years in the past, no observers existed to study the cosmos. We occupy a narrow slice of cosmic history when both observation and observers coexist, when evidence of the universe's origin and evolution remains accessible to creatures capable of understanding it. The cosmic microwave background continues fading. As the universe expands, this relic radiation redshifts to longer and longer wavelengths. Its temperature drops from its current roughly 3 degrees above absolute zero toward even colder values. Eventually, the signal will weaken below detectability. The baby picture of the universe will fade until no technology can recover it, erasing direct evidence of the Big Bang. Estimates suggest the cosmic microwave background will remain detectable for hundreds of billions of years at most. This sounds like an enormous timescale, and it is compared to human civilization or even Earth's age. But compared to the trillions upon trillions of years the universe might exist, It represents an infinitesimal fraction. Most of cosmic history will unfold without access to this crucial evidence. High redshift galaxies will disappear sooner. The most distant galaxies we currently observe sit near the edge of observability. As expansion continues, they will cross the cosmic horizon within tens of billions of years. Future astronomers will be unable to observe galaxies at redshift 10 or 12 or 15 because those objects will have receded beyond reach. The early universe will become inaccessible. Even lower redshift objects will eventually vanish. Galaxies we see at redshift 1, showing us the universe at half its current age, will cross the horizon too, given enough time. The ability to study cosmic evolution through observations of galaxies at different distances depends on a temporary state where expansion has not yet carried everything beyond view. That state will not last forever. The visibility of certain cosmological phenomena depends on lucky timing. Type Ia supernovae, used to discover dark energy, occur at specific rates in galaxies. As star formation declines in the future universe, fewer of these explosions will happen. Observing enough supernovae to measure cosmic acceleration might become impossible when star formation stops entirely. Future civilizations could miss the discovery of dark energy simply because the relevant stellar populations no longer exist. Metallicity provides another example. Studying low metallicity stars allows us to investigate the chemical composition of the early universe. These ancient stars contain few heavy elements, preserving signatures of the first stellar generations. But low metallicity stars are rare and getting rarer. Eventually, all pristine gas will be processed through stars and enriched with heavy elements. No new low metallicity stars will form. The window to study primordial composition through stellar spectroscopy will close. Humanity developed astronomy relatively recently in Earth's history. Complex life existed for hundreds of millions of years before technological civilizations emerged. Dinosaurs gazed at the same cosmic microwave background we detect, but they lacked the tools or understanding to measure it. Countless cosmic phenomena occurred during those eras with no one to observe or appreciate them. We arrived early enough to see distant galaxies, to measure the cosmic microwave background, to detect the signatures of the Big Bang, to map large-scale structure, to discover dark energy. A civilization arising trillions of years from now would miss most of these opportunities. They would observe a universe that appears static, isolated, and fundamentally different from the dynamic, evolving cosmos we see. This temporal asymmetry affects how we interpret observations. The data we collect now represents a snapshot of cosmic history at one particular moment. We cannot observe what the universe looked like trillions of years ago when it was younger than our current observable age because we did not exist. We cannot observe what it will look like trillions of years hence for the same reason. Our observations necessarily reflect conditions within a limited time window. The window is closing, not on human timescales. We have millions or billions of years remaining before Earth becomes uninhabitable or our star dies. But on cosmic timescales, the era when comprehensive observations are possible represents a fleeting moment, and that realization demands that we appreciate what we can see while we still can. We stand at the threshold of the observable universe, gazing back across 13.8 billion years of cosmic history. Light from the most distant galaxies left them when the universe was young, traveled through expanding space while galaxies formed and died, while our star ignited and Earth cooled, while life emerged and evolved into creatures capable of building telescopes to catch those ancient photons. We see the edge not as a boundary in space, but as a limit in time, a wall beyond which observation cannot reach. Everything we have discovered reinforces both how much we have learned and how much remains unknown. We mapped the cosmic microwave background and found the seeds of all structure. We detected dark matter through its gravitational effects, despite never seeing it directly. We discovered dark energy forcing the universe to accelerate away from itself. We found galaxies that formed impossibly early, stars made of pure primordial elements, black holes that grew to impossible sizes in impossible times. Each discovery raised new questions. Why do galaxies at high redshift appear more mature than models predict? What are dark matter and dark energy actually made of? How did supermassive black holes form so quickly? What physics governed the first moments after the Big Bang? We solved some cosmic mysteries only to uncover deeper ones hiding beneath. The edge of the universe teaches us about limits. The speed of light limits how fast information can travel. The age of the universe limits how far we can see. The expansion of space limits what will remain observable. Dark energy limits which structures will stay connected. Quantum mechanics limits the precision of certain measurements. Every frontier we approach reveals a new boundary we cannot cross. Yet within those limits, we have access to extraordinary information. We can observe conditions from when the universe was 380,000 years old. We can study the chemistry of stars from more than 13 billion years ago. We can measure the expansion rate to a few % accuracy. We can map structure across billions of light years. Humanity, confined to a single planet orbiting an ordinary star, has nevertheless revealed secrets of cosmic origin and evolution. The James Webb Space Telescope represents our current frontier of capability. Its infrared eyes pierce through dust and distance to reveal the early universe in unprecedented detail. But even Webb has limits. Fainter objects, more distant epochs, higher precision measurements. Each capability pushes observations marginally further but cannot break through the fundamental barriers imposed by physics. Future telescopes will continue the exploration, larger mirrors to gather more light, better detectors to measure fainter signals, longer wavelength coverage to see deeper into time, ground-based arrays working together as synthetic apertures spanning continents, space-based observatories at special orbital positions. Each generation of instruments extends our reach, but the ultimate limits remain. The real edge lies not in the cosmos, but in our understanding. Physical theories break down at sufficiently extreme conditions. Quantum mechanics and general relativity give contradictory predictions when both matter. The origin of dark matter and dark energy eludes explanation. The coincidences and fine-tunings that allow complex structures seem too perfect to be accidental. We glimpse outlines of deeper principles but cannot yet grasp them fully. Perhaps the lesson is that knowledge itself has edges, boundaries beyond which current understanding cannot penetrate. We must develop new mathematics, new physics, new ways of thinking to push past those boundaries. The universe offers clues scattered across its history, encoded in the light from distant galaxies, written in the patterns of cosmic structure, hidden in the quantum fluctuations that seeded everything. Humanity's journey to understand the cosmos continues. Each generation builds on discoveries made by previous observers, adding new data, refining old theories, sometimes overturning established models when evidence demands. We have come far from early humans who wondered about points of light in the sky. We know those lights are stars, galaxies, and quasars scattered across an expanding universe billions of years old. The edge of the universe is also a beginning. Every answer we find opens new questions. Every observation reveals unexpected phenomena. The cosmos refuses to yield its secrets easily, forcing us to work for every piece of understanding. And maybe that struggle, that journey from ignorance to knowledge, is part of what gives the endeavor meaning. We have found what NASA discovered at the edge of the universe: impossibly early galaxies, massive black holes, the limits of observation, the breakdown of physics, and the humbling recognition that most of reality lies forever beyond our reach, existing in regions we can never see, governed by principles we do not yet comprehend. The edge marks both how far we have come and how much farther the universe extends beyond our grasp.